In the last set of videos, we were looking at how to weigh stars. And the way that we looked at weighing them was as long as we knew some features, we could actually calculate the mass. And the mass of the star was actually found by this. If you remember the last videos here, was 4 pi squared over gt squared times r cubed. This right here was our sort of magic equation. Remember what everything here meant now. So m here is the mass of the object we're looking for. In this case, it's in kilograms. Don't forget that r, that's the orbital radius, because we're going to assume it's a circle, even though we know it's an ellipse. And we'll do the orbital radius in meters. And t, that's the orbital period. In other words, that's how long it takes to go all the way around in one circle. That's going to be in seconds. Remember that g is equal to 6.67 times 10 to the negative 11. So this method that we looked at before to weigh a star, we're going to use that same idea here. And this, I think, is really, really neat. So it turns out, we can use this method in a lot of other ways. So just to show you what we can do, we can find the mass of a planet. We can say is found by, in this case right here, we can say the period and orbital radius of, in this case, orbiting moons. Or we could even say, technically, we call those satellites. So anything that orbits it. So a moon is technically a satellite of the Earth. So as long as we can see, now keep in mind, I'm not just talking about a star anymore. It turns out this works more generically here. So if we have an object in the center, which we want to know its mass here, that's going to be its mass. And if we have something that's an orbit around it, whoops, maybe I'll use a different color to make it sort of the same that I've been using before here. Okay, this right here is the orbit. And if this right here is the radius here, and then we have the time, to go all the way around. As long as we have a central object and something go around in orbit, then we can use this here. So the mass of a planet, it turns out, as long as you have an orbiting satellite or an orbiting moon, you can calculate the mass of the planet by looking at orbiting moons or satellites. Well, you can also tell the mass of, well, in this case right here, we can say a star. That's what we just did before. Is found by the period and orbital radius of orbiting planets. And that's what we just looked at. And it turns out you can go further. You can figure out mass of it turns out we're going to call this a black hole. It can be found in this method as well. So it can be found by the orbital period and the orbital radius of orbiting stars. That's the sort of key thing here. Okay, is this right here. That if we have orbiting stars, then it turns out we can calculate the mass of the thing that's in the center. And I think this is just mind-blowing when I learned about this. So, turns out, in the center of our own galaxy, do you remember that we live in a big spiral galaxy here? We call it the Milky Way. And this has, hundreds of billions of stars. We're somewhere over here. Turns out if we look into the center at night, we actually see this sort of big streak across the sky here. It looks like milk being, poured across the sky, I suppose you could say. Now there's dust lanes in the middle here. There's lots of dust that's obscuring the light from the stars. But if you know where to look, if you know where the constellation Sagittarius is, turns out near the end here of the teapot of this Sagittarius, turns out that is the technical center of our own galaxy. Now it turns out in regular types of light, you actually can't see much. But it turns out if you use different wavelengths of light, which telescopes can do. Telescopes can look in radio waves, they can use infrared, they can use all sorts of different types of light that the human eye can't see. It turns out certain types of light, they go right through this dust. So using different types of light, this is what they saw. Now there were a whole bunch, this looks really complicated what you're looking at here, but what happened is this. They saw some stars. They named them, so there's S2, S14, S12, S1, S13, and so on. There's just a few examples here. And we're going to focus on S13. But it turns out all the other stars, if you took a picture of them one day, maybe the star is here for S14. And then, if, a year later, or I don't know what, sometime later you look and it's over here, and then it's over here, then it's over here, and then it's going back. In other words, this one has this type of orbit. Whereas S2 goes like this. And S13 goes like this. S8 goes like this. Now keep in mind it's not so simple because this is in 3 dimensions, so you have to imagine some of these things might actually be circles coming out of the page and into the page. But in any case, they saw orbiting stars. Now these stars were orbiting something in the middle that they could not see. The point is, when we're looking over here, we were looking at a planet. Oh, we know we can see the planet. And so we can see orbiting moons around it, and therefore we can calculate the mass of it. Just like we can see a star, we can see the planets, and we can do this. But it turns out you can do it for something that's invisible. So even if you can't see this thing in the center, they found a whole bunch of stars orbiting some unseen central place. So these were the coordinates of a central place here. And without going into too much crazy detail here, but it turns out what they did then is they just plotted these orbits of these different stars. And from there, it turns out we can just pick one star and then use that to calculate the mass of the thing in the center. Turns out you can use any of the stars for it. I thought I would use the one that's the most circular looking though. So S13. Now I haven't seen many people do this in a class, but I think it's pretty easy to do. I don't think there's much to it. So we're going to use the same idea. You are going to use the most circular looking orbit. By the way, for scale here, they show this that, see this here, if this center thing was the sun, see this little green thingy here, that would be Eris, or purple would be Pluto, which is a little bit inside there, Neptune. So it gives you an idea of the size of these things. So these things are in pretty big orbits. And yet, this particular star here, they're called S13, it has an orbital period of 36 years, and it has an orbital radius. Now remember, it's really an ellipse. But if we assumed it was a circle, it's got the equivalent to a circle that's got a radius of 1,750 astronomical units. In other words, 1,750 times what the Earth's orbital radius would be. So from that, let's calculate this central object here. So this is really what they did. They weren't sure what it was. They didn't know it was necessarily a black hole. This is just what they saw. At the center of our Milky Way galaxy, star S13 orbits an unseen object. Because you can't see the thing it's orbiting. It's just going around some point, which we can't see. Now the star we can see though. So the star has an orbital period of 36 years and an orbital radius of 1,750 astronomical units. And assuming a circular orbit, of course. What is the mass of this thing in the center? Well, we're going to use this same equation that we've been talking about here. So m is going to be equal to, we're going to use the same one here, so 4 pi squared over, and if we forget it, we can always go back, 4 pi squared over gt squared r cubed. So gt squared r cubed. All we have to do then is get everything in the proper units. So let's maybe work on the period here. So the period, which is 36 years, I need to convert that to seconds. So again, I can use this little trick here. If I would use something with years on the bottom, I know that there are 365 days in 1 year. If I do that, then I get the years cancel out. Now I have it, 36 times 365 gives me the answer in days. And again, I'm going to do something where I know how many days there are, and it turns out there's 24 hours in a day. That'll get rid of this. And I can do 60 minutes in an hour and then 60 seconds in a minute, or I can be a little bit lazier and say 3,600 seconds in 1 hour. That's the same. That's the same thing as saying 60 times 60. Well, then I'll use my trusty calculator here and do this number. So 36 times 365 times 24 times 3,600. This tells me what 36 years is in seconds. This is 1.1 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll say then that the period is approximately, well, we'll say it's 1.14 times 10 to the power of 9 seconds. I'm going to use that. That's going to be needed. that goes into here. Then I need to know what r is. Now my radius, orbital radius, in this case right here, was 1750 AU. Well, I have to know how to convert. It turns out there's a nice easy conversion. Turns out 1 astronomical unit is 1.5 times 10 to the 11 meters. That's really simple. So basically I just have to then take my, I'll just clear this here. All I have to do is take my 1,750 and multiply it by 1.5 times 10 to the power of 11. I get this number, so 2.63 times 10 to the 14. So r equals 2.63 times 10 to the 14 meters. That's obviously very big. See, when we talk about, a number being, oh, that's astronomically large. See what we mean by that? Because this is a very, very large number. Well, okay, but we're ready to do this now. So that means now we can go ahead and calculate this mass here. So we're ready. So the mass is going to be 4 pi squared divided by, and g, remember, is 6.67 times 10 to the negative 11. All that's going to be multiplied by 1.14 times 10 to the 9 squared. All that's going to be times 2.63 times 10 to the 14. All that's going to be cubed. And if we do it properly, then I'm just going to go through it fairly quickly. So here we go. I'm ready. I'm going to take this top number here. So 2.63 times 10 to the power of 14. I'm going to take that and cube it. I'm going to say that answer times 4 times pi times pi by itself, so 4 pi squared. It's that. I'm going to store that as top. I'm going to store that as A. That's going to be the top thing. And again, at the bottom, I'm going to calculate that. So 1.14 times 10 to the 9. I'm going to take that answer and square it. I take that answer and multiply it by 6.67 times 10 to the negative 11. Enter. And then I'm going to say A divided by this answer here. I can do it like that too. Now I get an answer of this right here. So I'm going to say this is 8.28 times 10 to the 36 kilograms. 8.28 times 10 to the 36 kilograms. That's maybe not very helpful. So let's look at what one solar mass is. Remember, we write the little symbol m with a little circle like this. One solar mass. And it turns out that one solar mass, this is important to know, it's around, we just calculated it, it's around 2 times 10 to the 30 kilograms. So I'm going to find out how many solar masses fit in this. So that means, therefore, the mass is going to be, well, I'm going to take this answer and divide it. I'm going to see how many solar masses fit in this. So I'm going to divide it by 2 times 10 to the 30. And if I do that, I get this. 4 times 10 to, well, 4.1, let's say, times 10 to the 1, 2, 3, 4, 5, 6. So 4.1 times 10 to the 6, that's going to be my number here, times 10 to the 6 solar masses. In other words, the mass of this thing is 4.1, remember what 10 to the 6 is, that's a million. So 4.1 million solar masses. So in other words, this central object, which we can't see, has a mass of 4.1 million times our own sun. So this thing is crazy big. In fact, it's not just called, well, let's look at this then. So we can take a look and say, well, what could possibly cause this? They didn't know it was a black hole necessarily until they calculated its mass and said, well, this thing is insanely massive, right? It's 4 million times the mass of the sun. And then they were able to look at this and say, well, we can constrain its size because we know it's smaller than the orbit of this one at least. So we know it's smaller than this. And it turns out with better and better results, they were able to constrain it even better. You can see some of these other orbits here. They're able to constrain its size to be less than 6 light hours. And it turns out the only thing that they could use to explain that density, the only thing that they could say has a mass of 4 million suns fitting in this tiny little place here, that has got to be a black hole. So this right here is why we call this right here a black hole. And so very sort of silly then, we can take a look at this silly joke. They say, well, it's black and it looks like a hole. I guess it's a black hole. So in the next video, we're going to look at a few interesting facts about black holes.